Dear learners, welcome to our week 3, lecture 3. In this lecture, I will explain that special cases of shells. Basically, we have developed a generalized governing equation. Actually, we have to work with like either cylindrical cell or spherical cell or conical or ellipsoid, whatever. So, we can convert this general differential equation to our special cases. So, I will explain with the help of example starting from the plate that how do we convert this partial differential equation to our depending upon the requirements. So, just have a look that these are the 5 differential equations. Equation number 1, equation number 2, equation number 3, equation number 4 and equation number 5. In some of the books this numbering may different because the 5th may come up to 3rd because after U, V, W comes then psi 1 and psi 2. Most important part is that even if you want to solve a nonlinear problem of a cell, first you need a solution of a linear differential equation. Then it will be acting as a initial guess and we can solve a nonlinear problem. So, very first approach is to go for a linear partial differential equation for the shell. So, if we remove these nonlinear terms, it will reduce to a first order shell differential equations, basically partial differential equation in which alpha and beta are do orthogonal curvilinear parameters. Let us say I want to find out the equation of a flat plate. Can I reduce or can I basically I would like to say not reduce, deduce that plate equation from our this cell governing equation. So, for the case of a plate, the parameter alpha is x and beta is y. And you know that ds square is dx square plus dy square and Lamé parameter a1 and a2 are 1. Radius of curvature in one direction and two directions are infinity. So, for making a special case we need at least means these I would like to say that how do we assign curvilinear parameter, that is the most important part, which direction you assign as an alpha and which direction you assign as in beta is very important. Then find out the Lamé parameters for that body or geometry, then find out the radiuses in first direction and second direction. If we have these parameters, see this is our main governing equation in which I have already marked, but I am going to explain it that let us say this first term n11 a1 and a2 are becoming 1 n11 a2 comma alpha. A2 is 1, okay, comma alpha means comma x. Now we have a second term minus n2 to a2 comma alpha means you have to take derivative of Lamé parameter with respect to first coordinate. So, a2 is 1, so if you want to take derivative it is 0, then n2 1 a1 comma beta. Next n1 to a1 comma beta. So a1 comma beta means again you want to take derivative of first Lemma parameter with respect to y, which is going to give you 0 plus q1 by r1. r1 is infinity, 1 over infinity is going to 0. So from a linear one these terms will not contribute. Again in this nonlinear terms 1 by r1 is here, so r1 is infinity, this will also not contribute, and the second term of nonlinearity will also not contribute, plus loading and dynamic inertia resultant. So 1 means x, or you can say that if you write n11 it is fine, if you want to write in terms of nxx that is also fine. So n11 comma x plus n21 comma y plus q1 equal to I naught u1 0 plus I1 psi1 0. Again if you are interested to write, you can write nx comma x plus nyx comma y plus loading in one direction equal to I naught u1 I1 psi1 double dot. Here I1 is going to be 0. The reason behind that, when you take for the case of shell, what is the definition of I1? I1 is minus h by 2 to plus h by 2. Then rho times zeta 1 plus zeta by r1 into 1 plus zeta by r2. So r1 r2 are infinity. So for a symmetric plate it will not exist. So it will be just I0 and u1 0 double dot. Now come to the second equation. In second equation first term will not contribute because a1 is constant, second term will contribute, similarly third term will not contribute and fourth will contribute, and q2 by r1 will not contribute. Same way the nonlinear terms will vanish. So we will get the terms like this. Then come to the third equation. In third equation first term will not contribute, second term m11 a2 comma alpha will contribute plus m21 a1 comma beta will contribute, and this will also q1 will remain. So here there is in the even the shell equation there are no nonlinear terms. So this equation becomes like this. Then the fourth equation, here m22 a1 comma beta will contribute and m12 a2 comma alpha will contribute. That is equal to q2. When you come to the fifth equation, if you see that first we have put the nonlinear terms, then the linear contribution. Here in the nonlinear contribution, this single term that a1 u1 0 by r1 will not contribute, but definitely these nonlinear terms will remain. Then next this will not contribute and they will remain. Same way n hat 2 and n tilde 2. So you see that in the fifth equation we will have some nonlinear contribution for the case of rectangular plate, and these terms will not contribute, only they will contribute. So q1 comma x plus q2 comma y some nonlinear term plus q3 is, if you want to, it is basically for a dynamic it will be I0 w double dot. If you want to say that we do not want dynamic, then you can reduce the dynamic also. So nonlinear contributions are expressed like this. So if you try to verify, these are the same equation of partial differential equation for the case of rectangular plate under FSDT, first order shear deformation theory. So, you will get a similar set of boundary, like first equation is nxx comma x plus nyx comma y. If we say, let us say only for static case, just for simply static case and only transverse loading. Generally most of the books they consider only plate under transverse loading bending case, then it will be 0 and then nxy comma x plus nyy comma y is going to be 0, then mxx comma x plus myx comma y minus q1 is going to be 0, then again mxy comma x plus myy comma y minus q2 is going to be 0, and already we have written that q1 comma x plus q2 comma y minus q3 is going to be 0. So, for a plate under transverse loading, static bending case, you can find these 5 set of governing equations. You can verify where q1 is this, q2 is this. If you substitute it into this equation, so basically it reduced to a classical plate theory. So, it gives you mx x double derivative of x plus twice of mxy comma xy plus myy double derivative of y minus q3 is going to be 0. So, this is your third equation for the case of CLT, and this is your second equation and first equation. So, for the case of plate, we can able to deduce the set of governing equations. For the case of FSDT 5 equation, if you want to know for a classical shell, then you have to use these 2 equations and substitute in the 5th equation, and final equation can be obtained. So, from this what you have learned? You have learned that we have developed a generalized partial differential equation for a doubly curved shell. Now, depending upon our requirement or upon our application, we can deduce or we can get our governing equations. Now, the questions comes here that we have derived by taking the assumptions of first order shear deformation shell theories, like we have assumed our displacement field u10 plus zeta times of psi 1. If you want to do for a third order or if you want to do for a higher order theories, then first you have to develop a higher order model, and then later on the lower order model can be obtained as a special case. For example, in this case that first order shear deformation theory we have developed. So, we can get a special case like classical shell theories or classical plate theories, that lower order can be obtained by putting some index. Now, I am going to explain how do you derive or deduce that set of equations for a circular plate. If you take an example of a circular plate, then if you want to take a small element, let us say at distance r, and that distance will be dr and this will be d theta. So, in that case our ds square will be dr square plus r d theta. So, from here A1 is R1 and A2 is R, and alpha curvilinear parameter first is R and beta is theta. Basically in polar coordinate we are talking about R and theta. For the case of a circular plate, the radius of curvature R1 and R2 are infinity. Because this is a flat only, sometimes you may say it is curved in that direction, but we are not taking that as a curvature. So, from that it is basically a longitudinal sense. So, R1 and R2 from this and this side, it is going to give you basically bottom one and side one. R1 is infinity and R2 is again. So, if you want to compare, like if we have a cylindrical shell, then you can see that from bottom side and this side. So, from bottom shell is cylindrical, but for the case of plate, if you see from the bottom, it is a flat piece. So, R1 and R2 are infinity for the case of circular plate. So, in this equation, that R1 and R2 are infinity. So, straightforward we can say that Q1 by R1 will not contribute. Similarly, these nonlinear terms will also not contribute. Definitely in the linear terms, we have to see that first 1 by A1, A2. So, A1 is 1, A2 is R. So, it becomes 1 by R, then N 1, 1. So, alpha is our R and beta is our theta, or we can say that 1 is our R and 2 is our theta. So, NRR, A2 is R, derivative with respect to R, definitely it will exist. Then A2 comma alpha, R comma alpha. So, basically A2 is R. If you want to take derivative of A2 with respect to alpha, R तो क्या होगा? It will be a constant 1. Yes. So, this term will contribute here, and 2 means n theta theta, A2 comma alpha will give you 1. Then come to N2 1. In N2 1, n theta r. A1 is 1 comma beta means comma theta. N1 comma A1 comma beta. A1 is 1. If you want to take derivative with respect to theta, it is going to give you 0. So, 3 terms will contribute and first equation can be obtained like this. And these are your dynamic terms and loading. Similarly, from the second equation, that first term will not contribute, second term will contribute, third term will contribute and fourth term will also contribute. Let us see, this is n theta theta comma theta. This is n theta r 2 comma alpha, that gives you 1 basic. Then n 1 comma 2. Here n theta r and n r theta are same. I would like to point out however there that n r theta equal to n theta r. The reason behind that, because the only difference because of z by r1 terms or 1 by z by r2. So, here R1 and R2 are infinity, so they will not create a difference. So, n r theta or n theta r are same for the case of circular plate. So, we can write n r theta. Next, n r theta A2 comma alpha. So, A2 is R and derivative with respect to R. If you want to verify or you want to look, so you can look any plate and shell book in which the circular plate is discussed, you will find that first equation will look like this and second equation will look like this. Now, come to the third equation. minus m theta theta, a2 comma alpha will give you 1, then m11, mrr, r comma r, then m theta r comma theta, and a1 comma beta will not contribute, minus qr. Then similarly, fourth equation, that first term will not contribute, these three terms will contribute. So, we can get m theta theta comma theta, then m r theta plus m r theta r comma r, minus q2 or q theta. If we are writing in a proper sense, then it will be q theta equal to your dynamic contribution like I1 U2 0 double dot plus I2 psi 2 double dot. Now come to the fifth equation. Here again this term will not contribute, this term will not contribute, this term will also be 0, and again this term. So, first term will be 1 by r, a2 is r. So, n hat hat r w comma r whole derivative r. So, this will be the contribution of a nonlinear term. In the next, n hat theta theta 1 by r and w comma theta with respect to theta. In the third term, n tilde 1 to w comma theta whole derivative with respect to r and whole derivative with respect to theta. Next basically, plus they will not contribute. Here q r comma r upon में r. So, 1 over r q r comma r plus q theta comma theta upon r. So, basically r is not a function of here 1 over r and here 1 over r will also come up. So, finally, I have written the final set of governing equations which we have deduced from the shell will look like this. So, for this case also, that I1 contribution will not be there, and final the contribution of fifth equation will be look like this. So, this is the same governing equations. The purpose of explaining is this, that once you get a governing differential equation for a generalized shell element, then for the lower order, like whether you talk about a plate or you talk about a circular plate or you talk about a cylinder, you can derive their governing equation. So, you need not to again. So, sometimes for the case of development, it will be a special cases, that if my delta is, or the request is that can we get the solution for a circular plate? Yes, first you have to convert from the basic equation to a circular equation and then you can solve it. The next most important, I would like to say that is our purpose, because circular plate and the rectangular plate, they are the easy one that we can derive, but definitely that in cylindrical coordinate system, circular cylindrical shell. Why I have written that circular cylindrical shell? Because in this shell theories, you may have a number of cylinders with having different this face, like it may be circular, sometimes they may say it may be oval or it may be elliptical. So, you will have different A1 and A2 for that. So, the very simplest case is the circular cylindrical shell, and in most of the literature or the books, they have covered that. Even I would like to say that most simplified one is circular cylindrical shell, and the most of the solutions, analytical solutions are available for this case. If you want to go for a typical or a very different kind of a geometry, definitely one can go ahead for the depending upon the requirement, but in 90% cases this we try to see that in our day to day life or in a structural application, that circular cylindrical shell. Odd shapes definitely one can try. So, for that you have to obtain proper A1, A2, R1 and R2. So, for this case alpha is x. X is not just it is the length along that direction, and beta is along the circumferential direction, theta direction. So, if you cut a cylindrical element and if you see from the bottom, you will find a radius is there in that direction, and the longitudinal direction, the lengthwise there is in second direction infinity. So, if you want to write, so A1 is 1, A2 is R. Generally we represent with the capital R. In the case of a circular plate, we represent this with a small r, and here R1 is infinity and R2 is R. I would like to say that mathematics point of view, from a circular plate to a cylindrical shell, the difference is here that here radius in second direction exists, that is R. This is only one parameter is changed now. Previously, if you see that from a rectangular plate, A1 is 1, A2 is 1, R1 is infinity and R2 is infinity. So, for a circular plate this becomes R, second change, and third change, okay, it remains same, now radius is there. So, one by one, so you have seen that the major difference when this even A2 is R, your governing equations looks entirely different compared to a flat rectangular plate. Now, if you include this effect of radius, then all this set of governing equation will be entirely different, or it will not look similar like a plate. So, let us go. Here 1 upon my A1, A2. So, we will write it here 1 by R and then N1, 1. So, Nxx A2 is R comma alpha comma R, capital R comma X, alpha X. Then N2, 2, A2 comma alpha means A2 is R and with respect to X. So, that will not contribute. A2 comma alpha, R comma X, R is not a function of X. Then N2, 1, N2, 1 will be N theta X, A1 is 1 comma theta. Then this term will also not contribute. So, from here one can see that, wait a minute, A2 comma alpha, where I have written something, A2 is R. So, A2 comma alpha means A2 with respect to X, it will not contribute. So, this term will not be there, Nxx whole derivative comma X and N theta comma theta. Then I will have to check it, this equation. So, I will clarify in the tutorial part or the next lecture. Then we have a second equation 1 comma beta. So, definitely 1 comma beta will not contribute, but here N theta theta comma theta and A2 comma alpha. So, it will also not contribute and the second term will come up. So, this is definitely going to be 0. So, we are going to have these things. That comes through basically from that linear theory from there, and we have to see that n2 to a2 comma alpha n theta theta comma x, it is not there, so it will not come. I have written next n theta x comma theta. Actually, in some of the book, the concept of thin cylindrical shell, there we have a extra term, if you remember, that m tilde 1 to c naught. So, m tilde 1 2 having a contribution of n theta theta and so on. So, then these terms will contribute. Otherwise, for a thick shell, this term will not contribute. And then we have this equation. Second equation. So, in the first equation, q1 by r will not come, but in the second equation, r2 is there. So, it will contribute. Then some nonlinear term will also contribute because r2 is there. r1 is infinity. So, in first equation there will be no nonlinear term, but in the second equation nonlinear term will contribute. So, we will consider these things because r2 is now non-zero. In the next third equation, if you get it from there, that this will not contribute, only these two equations, two terms will contribute. So, it will be mxx a2 is r comma x plus m theta x a1 is 1 comma beta means theta minus q1 equal to this. So, here you see that r is not a function of x. So, you can take common out. So, ultimately it will get cancelled out from the outside and it will contain 1 by r mx theta comma theta minus q1, or you may say that qx equal to this much. Then come to the fourth equation. There also it will not contribute, this will not contribute, only these two terms will contribute, m theta theta comma theta and mx theta comma x. So, 1 by r, and here r is inside and r is outside. So, this r will get cancel out and q2 is basically q theta, and this is the fourth equation. And in the fifth equation, definitely some nonlinear terms. This term will not contribute, this term will not contribute, they will contribute fully. So, partial terms are here. Then this term will not contribute, this will contribute. Again here we have to contribute. So, qx, so a2 is r, r is not a function of x. So, it will come outside and 1 upon r, that will get cancelled out. Then this one a1 is 1, 1 by r q theta comma theta minus n theta by r minus q3 plus some nonlinear terms equal to dynamic. So, in this way we have deduced that governing equations for a cylindrical shell. So, in some of the books, that thin cylindrical shells, that equations are deduced and problems are solved. So, but they are very special ones. So, already I have given the treatment that for a thin cylindrical shell, in first and second equation we add a term that a1 c0 1 by a1 c0 m tilde 1 2. So, in the first equation we add, in the second equation we minus it. So, if we consider these terms, then in this equation that will be valid for a thin cylindrical shell. Now, the most I would like to say that useful, that shell of revolution. So, this is the most generalized form, that any means we have already classified the shell, that one the first classification by that surface of revolution. Then the we can generate the surfaces by translation through a parametric line. So, very first classification, that most of the shells can be, or shell surfaces can be generated through the revolution about the meridian axis or about the central axis. So, in that case it is with the general one, that doubly curved shell, that it will have curvature in both the directions. Let us say alpha is phi, and because our coordinate system is beta here, beta is theta. In some of the books the coordinates are alpha 1 and alpha 2, but in this course we have taken alpha and beta. So, alpha is phi and beta is theta. So, if you see that the surface of revolutions and you see these parametric lines, so we will have one horizontal circus. So, it is going like this, and parametric lines from top. So, we will have two radius of curvature, one along this, one along this. So, if you take an cell element and if you see from the bottom, then one radius of curvature along this horizontal one will be for a vertical one. So, if you take a shell element like this, then the length of that cell element along this, it will be r1 times of d phi, because this angle is d phi. Then this angle is d theta, that which is making on a horizontal one, then d SAC will give you r naught, that is r naught times of d theta. So, r naught is again can be expressed in terms of r2 sin phi, where r2 is making with that. So, here r1 and r2 are radius of curvature, where small r1 is kept. Generally the formulation is done in terms of small r1 and r2, but at the end of the day that radius of curvature they are related to r1 and r2. So, from here alpha is phi, beta is theta, a1 is now r1, or you can say just capital R1, and a2 is r2 sin phi, or you can write capital R2 sin phi. Sometimes we also note it as r naught. So, with these parameters I am going to deduce that first I will explain that how to work with this first equation. Till now it was very comfortable that in first equation 1 by a1 a2. Now here let us say a1 is our r1 and a2 is r2 sin phi. So, in the bottom coordinate r sin phi comes into the picture. So, if this is the situation, we do not want that some trigonometric terms at the bottom, maximum we can have only the radius one. So, we have to first convert into the normal form, so that we do not have a1 a2. So, we will say a1 a2 multiply with this q1 1 a2. So, it will go to the multiplication. If you remember, initially this a1 a2 was with q1 and small q1. Initially whatever we have obtained from that weak form of integrals, then it was a1 a2, and after that I put here. So, we have to put it back here. Now, we can start working with this. The one important point is here, if you want to know that a1 comma phi or a1 comma theta, then a2 comma theta, then they will contribute a 0, but a2 comma phi, so d2 a2 by phi, this is r2 sin phi. So, using the concept of Gauss-Quadratic equations, that gives you r1 cos phi. So, the detailed derivations of doubly curved system can be seen in the book of Thin Plate and Shells by Edred Wenzel and Theodore. The page number is 318, chapter 11. So, this derivation is basically about this derivation is given, and in I think chapter 16 or chapter 14 this complete derivation is given there. So, we can say that n phi phi r naught a2, for a simplified one we can say r naught, or you can write r2 sin phi comma phi. Then a2 comma alpha, a2 comma alpha, alpha means phi. So, it will be n theta theta r1 cos phi. Then n21 a1, then n phi theta comma theta plus 0 plus, okay, this will not contribute, this will be 0, a1 comma beta. So, q1 by r. So, basically ultimately if it is r, so a1 a2 goes up here and r1 here. So, a1 is r1 and a2 is r2 sin phi. So, r2 sin phi, r1 get cancelled out and this one is q1 and then the dynamic terms. So, this is the form of differential equation for the case of doubly curved shell which is having surface of revolution. So, if r1 equal to r2 equal to r, then we can get these equations for the case of spherical shell. Otherwise, the shell may have like ellipse kind of thing or some different shell surfaces. Same way, we can get the set of equations in the second direction, and then third and fourth direction. So, I would like to say that q2 by r2 plus q2 r1 r2 sin phi plus some dynamic terms. Again here a2 comma alpha, so it will exist. So, it will be m22 means m theta theta, a2 comma alpha means r1 cos phi plus m11 m phi phi, a2 means r1 sin phi comma phi plus m21 m theta phi, a1 is now r comma beta means theta. a1 comma beta will 0, it will not contribute, minus q1, here is it is just q1. So, q1 into a1 a2, so it comes r1 r2 sin phi, there is no and dynamic terms. Then come to the, this will not contribute, this will contribute and this will contribute. So, basically m theta theta r1 cos phi plus m phi theta r1 sin phi comma phi minus q2 r1 r2 sin phi, sorry r2 है, r2 sin phi, a2 is r2 sin phi is equal to some dynamic terms. And the fifth one, so if you put n11, again in fifth equation we have to do some mathematical simplification because it is coming at the bottom. So, we have to multiply it here. So, a1 a2, so r1 will get cancelled out. So, n11 r2 sin phi minus n22 r1 sin phi, then q phi r2 sin phi comma phi plus q theta r1 comma theta minus q3 of r1 r2 sin phi and loading term. So, once we get this set of equations, Now the questions comes, can we solve the problems? Can we get our displacements? Our aim is to find out the displacement, stresses, moments. So can we directly work with these equations? We cannot directly work with these equations because they are in stress resultant form. Whether you talk about cylindrical shell or a complete shell or any kind of shell, we have to first convert into a primary displacement form. So, our primary displacements are u10, u20, then we have w0, then psi 1 and psi 2. So, for this very first approach step is to find out a cell constitutive equations like epsilon ij s ij kl sigma kl is known as generalized Hooke's law or 3-dimensional constitutive equations relations basically. They are for a 3-dimensional body. Now we have to find it out for the case of shell. So, in the very starting for a moderately thick to thick cell, we assume a concept of a plane stress. Under that head, sigma 33 is considered 0. So, if we choose like that, then the stresses sigma 11, sigma 22, tau 12 can be expressed in terms of a matrix Q and strains, where Q, Q11, Q12, Q22 and Q66 are known as reduced stiffness coefficients, and in the case of shear tau 23 and tau 13 are expressed with the help of a Q44 and Q55. Now, how do you get a constitutive relations for the case of shell? Then we say that the definition of N11 stress resultant in first direction is minus h by 2 plus h by 2 sigma 11 1 plus zeta by r2 into d zeta. This is our definition. We know that sigma 11 using the constitutive relation of a material, we can get q11 epsilon 11 plus q12 epsilon 22 1 plus zeta by r2 zeta 2. In the plate it is very simple, but for the case of shell it is not very simple, I would like to say that slightly complex. So, epsilon 11 is what? Epsilon 11 is 2 component, 0 component which is causing the membrane and epsilon 11 component which is causing the bending in the shell. Then similarly epsilon 22. Now we have a component 1 plus zeta by r2. The rest of the equations N22 and so on I will cover in the next lecture. Thank you very much.